let me start this with an example. What do you mean by Lorentz transformation of field? You have two parallel, you are having two conductors, let's say, and they are carrying current in the same direction. Okay? You have two wires, let's say, they are carrying current in the same direction. So what will happen to them? What will happen to them? Okay, if they are going in the opposite direction? If the current is going in the opposite direction? Either they can attract or repel each other, is it? So why it happens so? Okay, so when something attracts, let's say two wires are attracting each other, is it? Can you think that attraction is a work done?
Yes, sir.
Because once it gets attracted, so it will get displaced in this direction, is it? Okay, so that means there is a work done on this very conductor, is it? But how you can explain this kind of work done? You say magnetic force, magnetic field does no work. That we have seen, is it? How you can explain this kind of work done? Or why they have to attract each other or repel each other? What makes them to do so? Have you, yes? Okay, when you say they attract each other, is it? Okay, what kind of argument do you put? Yes, what is an argument you are making? Any idea? So you calculate simply the magnetic force, is it? Because of the field, you calculate actually the force, and you see the direction of the force is this. Simple, the vector rules, is it?
Yes, sir.
Left hand thumb rule. So you see actually the magnetic line, let's say. So you are having magnetic lines of force this way. Okay, these are the magnetic lines of force, and you say this is the argument usually you put. So you are having the force on this very conductor due to this very field in this direction, and the force on this conductor due to this, so it is actually in this direction. Then you say actually the force points opposite to each other, so you say they attract it, they should attract it, is it? And but if force points like say this way you say this is the argument you are putting, is it? Is this argument true? You can show it geometrically, it's okay, but what is the physical understanding behind this kind of argument? Okay, so you can think, so you are having an observer. Okay, so this is actually we are going to do. You can think them to two observers, okay, or two frames of references. Okay, this observer is looking at this observer. Okay, let's say if this is a purely magnetic field here, so what this observer can observe, is it? So or what you can observe in this frame of reference, or if this purely electric field, what this observer can observe. So these are two frames of references, and we need to actually understand how field transforms between the two frames of references. Okay, how they are related if you are having two frames of references, how the fields, electric and magnetic field, are related to each other. Okay, got it? So this is our problem, and once we figure out how they are related to each other, okay, then we can understand why they have to attract or why they have to repel. Okay, that means there is some force of attraction or force of repulsion. In other words, there is some sort of work done, is it?
Yes.
Okay, what makes it to do so? Samajh? Okay, now let's try to understand first how fields transform. Okay, so how we define our electromagnetic field? We define it by this 4 vector, is it? So phi vector E. Clear? Is that true? So it is phi AX, AY, AZ. Let me write this way. And you are having A mu as phi and minus vector A. So that's phi. So this is how we write the electromagnetic field. Now these are actually the components of a 4 vector. When I define a 4 vector, it means its components transform in the same way as the coordinates are transforming. Okay, under Lorentz transformation. Okay, let's assume the boost along x direction. So you are having boost along x direction. What are your Lorentz transformations? X prime is equal to, tell me, gamma into x minus vt. Is that true?
Yes, sir.
Okay, then sorry, okay, it's x prime. Let me write. Okay, let's write x prime. Then you are having y prime same as y, z prime same as z, and t prime is equal to gamma into t minus v by c square x. Is this the way? So these are Lorentz boosts. I'm not putting in the 4 vector notation. Okay, so what does that it mean? So I am having a 4 vector. Now what does it mean? So a mu is a 4 vector, is it?
Yes, sir.
So it means its components will transform in the same way as these are transforming. So this is your temporal component, and these are what? Spatial components. Okay? So Samashavan? Okay. So let's write then. So I can write now this phi, since it's a temporal component, phi prime will be same as some gamma minus gamma into phi minus, let me write this way, beta ax. And this way, what's our gamma? 1 by root of 1 minus v square by c square. What is beta? Tell me. V by c. So it will be in this fashion. Huh? Okay? So you need to put it in what? So you multiply by this c, so it will be c here, so it will be simply what? So then this is your x naught, x naught component, x naught minus beta x. Clear? So now let's write ax. So ax prime will be as gamma into ax minus beta phi. Clear? And your ay, since I am considering the boost along x direction, these will remain unchanged. These are the components of the 4 vector. Clear? Got it? Okay. So now how you calculate the field from, if you know A and phi, how you calculate the field? So you calculate now field as minus gradient of phi minus 1 by c partial A by partial t. Clear? Is that true? Okay. And how you calculate B? Curl of A. Okay. So I can write it in this fashion. So let's start from the primate coordinates. So you can write E prime as minus nabla phi. So this will be always also in the primate coordinates, because gradient will change when you move from one coordinate system to another coordinate system. It will be like this thing in a primate coordinate system: phi prime minus 1 by c partial by partial t prime a prime. And similarly with the B. Okay. So now you substitute what is your phi prime. So this is your phi prime, and what is your A prime? So you can calculate it, let's say Ex. Okay, let me give you a hint how to do it. So you can calculate Ex, let's say Ex prime. So it is minus x component of this thing. It will be partial by partial x prime. Okay. Well, let me write that. Let's calculate the Ex prime. So it's minus partial by partial x prime phi prime. Okay, I'll be doing it in a different way. Okay, I am just giving you a hint how this can be. This is very complicated to in this way. Rather laborious, not complicated, laborious. Okay, we need to figure out a smart way. Okay, so you need to know how partial. Okay, how this partial by partial x is related to the unprimed coordinates. Is it? Got it? And you know how phi prime is related to the unprimed coordinates, and also you know Ax prime, and you need to figure out how partial by partial t prime changes. Okay? And then you make the differentiation, ultimately you get Ax prime. Is it? Clear? Till this point? But do you think so it's a laborious job? You need to figure out derivatives and so on and so on. Okay? So this will be a home assignment for you people. Just do it. It's a simple exercise, a lengthy exercise. Just do it. calculate the components Ex, Ey and Ez, similarly Bx, By and Bz. Just do it, okay, at your place. This will be only the exercise from this topic, okay, but I will do it in a different fashion, okay. That is actually a simple way to do it. Okay, now tell me, what is the quantity we know which contains both electric and magnetic fields? It is the field tensor, F mu nu. True? If I know the transformation properties of F mu nu, I know actually the transformation properties of what? Fields, its components. So I will just figure out what are the how F mu nu transforms under Lorentz transformation. Okay? So if once I figure out that, so I will just write then the components. Clear? Okay, so let's write. Okay, so you are having this vector. Let's take this x prime mu. Under Lorentz transformation, it transforms this way. Lorentz transformation matrix, lambda mu nu, x nu. Is it? So it's a tensor of rank 1. It's a vector, that means tensor of rank 1, is it? So now if I write now tensor of rank 2, so your F mu nu, clear? So how it will transform? So that means each index will transform in this way. So for every index, you will be having this matrix lambda. Okay, let me write it. So in the primary coordinate system, so I will write lambda, put this very index here, then you are having another lambda, let's write this nu here. Okay, so why it has come from some f, let's write lambda sigma, so put lambda sigma here. So is this the way? And now you are having a rank 2 tensor, it will transform this way. So each index, so mu index, so this, for each index you are having this lambda matrix. Okay, so for this new index you are having this matrix. Clear? If you remember, when we are doing the transformation properties of tensors, how the way we define the tensors. Okay, so we started with, let's say, some vector. Okay, there. Okay, let me write. We start with this ai, some vector. How we define it? Partial xi by some partial x prime j. Okay, then you are having this aj. Is that true? So then we put, if we are having, let's say, aik for each index. Okay, so it is in the primary system. For each index, what do you do? You put this kind of factor, is it? You remember? Okay, like this thing. Let's write L and A. Clear?
Yes, sir.
You got it? So that means for each index, you are having this kind of matrix. Huh? Clear?
Yes, sir.
Okay. So this is how for this rather a tensor of rank 2. This is an antisymmetric rank 2 tensor. Okay, rather a 4 tensor I should say, because this mu contains how many components? 4 components. So mu goes from 0 to 3. Okay, and mu goes from 0 to 3. The way this is a 4 vector, so you can think this also as a tensor, but these indices are not infinite in nature. They are only the finite values. Okay. Okay, so let's write now. So this is now the transformation rule of what? So if I know now the matrix is lambda, so what I will get? The components of this F. Clear?
Yes,
Samajh? So how I will choose? Let's write boost along x direction. Let's take boost along x direction. Can anybody tell me how this lambda looks like? Let's write lambda mu nu. So anybody? Don't. Okay, so this lambda, so these are not the same. This in this here. Okay, so here let me write some alpha beta. So lambda alpha beta. Just tell me what is this matrix? Anybody? So this is gamma minus beta gamma 0 0. The same thing. Okay, minus beta gamma gamma 0 0 0 0 1 0 0 0 0 1. Okay, now let's write lambda Okay, tell me what is lambda 0, 0. So lambda 0, 0, lambda 1, 1, they are what? Equal to gamma, is it? Lambda 0, 0, this lambda 1, 1. And then you are having lambda 2, 2 is equal to lambda 3, 3, those are equal to 1. Identity, is it? So I have figured out now the components. Okay. Similarly, you are having now lambda 0, 1. Look here. So you are having lambda, what is this? Lambda 0, 1, is it? And what this object is? Lambda 1, 0. So that is same as lambda 1, 0. What is that equal to? Minus beta gamma. Clear?
Yes, sir.
Okay. Okay. So all others are what? All others are 0. So these are only non-vanishing. Now let's go back to this very relation, this very equation, all this equation first. Okay? So what are the, if I take 0, 0 element, f 0, 0, that is 0, f1, 1 is 0. So we are having these diagonal terms are what? If you remember, what are they? What are these things? So that's 0. Diagonal terms. So I don't need to figure out their transformation rule, is it? So what I will do, I will just look at 0 and ith element. Okay, or 0 and nth element. Rather ith element. I will put now f0i. Okay, what is I? So 1, 2 and 3. If I, let's say if I put simply mu, so it will be f0, 0. Clear? So let's say if I put like this way, that's right. If I put f0 nu goes from where? 0 to 3. So but 0 means f0, 0, is it? That's x0. So that's why I will put only this kind of indices. So now let's write this lambda. Okay, look at the lambda. So what you are having? Mu I have put 0, is it? So nu I have put I. Clear? So you are having this 0 and these are as such. So this is I sigma f lambda sigma. Clear? Understood?
Yes, sir.
Huh? Any problem? Shall I repeat? Okay. So now let's evaluate this very sum. So there is a sum over lambda and sigma. Okay, these are contracted indices. Okay, so let's evaluate. Let me write for you people. I mean, let me do step by step. Let's evaluate only sum over sigma. Clear? First, we will do sum over sigma. Okay, let's write. So it is lambda I sigma. What is where from sigma goes? 0 to 3. So it will be 0 f lambda 0 plus lambda I 1 f lambda 1 plus lambda I 2 f lambda 2 plus lambda I 3 f lambda 3. Clear? So how many terms I am having? 4 terms. Now there is a sum over lambda as well. Is it? So how many? So from this very term I will get 4. From this I will get 4. From this I will get, so total 16 terms I will get. Let's write step by step those 16 terms. Let's take this very term first. Okay? Let's take this very term. Okay. So there is a sum over lambda, is it? So let's write. So it is lambda 0, 0. Because lambda goes from 0, so it is lambda 0, so 0. So lambda, this will not change, this will be as such, f0, 0. Clear? So then I am having lambda 0, 1, okay, lambda I 0, f1, 0. So I am taking the first term, okay, and summing over the lambda, plus lambda 0, 2, lambda I 0, f2, 0, plus lambda 0, 3, lambda I 0, f3, 0. Clear? So the 4 terms from the first term. Okay? Then, so I am having, now let's take this very term, this and this thing. So sum over lambda. So I am having lambda 0, 0, lambda I 1, f0, 1, plus lambda 0, 1, lambda I 1, f0, sorry, f1, 1. So, okay, plus lambda 0, 2, lambda I 1, f2, 1, plus lambda 0, 3, lambda I 1 F35. Clear? You people are following it? Okay, good. Plus lambda 0 0 lambda I2 lambda 0 2 plus lambda 0 1 lambda I2 lambda 0 lambda 1 2 plus lambda 0 2 lambda I2 okay F2 2 plus lambda 0 3 lambda I2 F3 2. Okay, this is the term. Then you are having the last term. Okay, let me write last term here. So you are having lambda 0 0 lambda I3 F0 3 plus lambda 0 1 lambda I3 F1 3 plus lambda 0 2 lambda I3 F2 3 plus lambda 0 3 lambda I3 F3 3. Clear? Okay. So let's keep only these terms here because I require them. Okay. So now let's look at these very terms in detail. Let's look. So this very term is 0. F00. Is it true? F00. Then you are having F11. This is 0. Okay. Then you are having F22. This is 0. F33. This is 0. Clear? Samashama? Okay. Now tell me. Okay. Lambda 0 0 is non-zero. Lambda 0 1 is non-zero. And what is lambda 0 2? Lambda 0 2 is 0. Is that true? So lambda 0 2. What is lambda 0 3? This again 0. Because the matrix what we have written for the boost along x direction, we don't have these components. Clear? Okay. So now tell me, what about this lambda 0 2? This lambda 0 2? This again 0. Because lambda 0 2 is 0. Lambda 0 3 is 0. Clear? So this lambda 0 3, this is equal to 0. Okay, lambda 0 2, this is equal to 0. Then, okay, so lambda 0 2, this is equal to 0. This f prime 0 I. Now tell me term by term. Okay, what is lambda 0 0? Okay, let's write for the lambda 0 0 lambda. Okay, so the first term is 0. So what is the next term? So it is lambda 0 1 lambda I 0. Then what you are having? F1 0. Okay, so in the first row there is only one term which is non-zero, and in the second row what I am having? Tell me. Lambda 0 0. Okay. Lambda I 0 lambda I 1. Then you are having F0 1. Clear? So you are having this very term. In the next row there are two terms. So lambda 0 0 lambda I2 F0 2 plus lambda 0 1 lambda I2 F1 2. True? Then in the last row what I am having? Lambda 0 0 lambda I3 F0 3 plus lambda 0 1 lambda I3 F1 3. Rest are 0. Clear? So that means what is this F0I? So it is ith component of the electric field, because F0I represents the electric field. So it is the ith component. That means ith component of the electric field changes in this way. We need to figure it out. Okay. So let's take I is equal to 1. That means x component. Okay. So let's take I is equal to 1. So what you are having? F prime 0 1. So that's equal to, what is lambda 0 1? Tell me. So it's minus beta. Okay, let me write lambda 0 1 lambda 1 0 F10. Then tell me plus lambda 00 lambda 11 F01. Okay. Now if I write here, look here, if I put I is equal to 1, what is lambda 12? That is 0. You don't have lambda 12 term. You don't have lambda 12 term. You don't have lambda 13 term. You don't have lambda 13 term. Clear? Shall I write these terms explicitly, or I will keep them there? Okay. Okay. So others are 0. Others are 0. Okay. Clear? So that means only the first two rows contribute. The second two rows does not contribute. Okay. Now what is lambda 01? It's minus beta gamma. This is minus beta gamma. What is F10? Okay, let's write. So let me keep it as F10 plus what is lambda 00? It is equal to gamma. What is this lambda 11? Lambda 11 is again gamma. So it's gamma into gamma F01. Okay. So I will write it. What is F10? It's minus times F01, is it?
Yes, sir.
So if I write F01, that's equal to minus F10. True? Okay, so you can put this as in terms of F01, or you can put this in terms of F10. Let's write F10 this way. So it is beta square, gamma square, okay, minus gamma square. So what this object is equal to? Anybody? This equal to 1. Is this equal to 1? Okay, so this is equal to minus 1. Nalaiko. Okay, so it is F10. So what is beta? Okay, what is beta square? So it is V square by C square minus 1. Is it? Okay, what is your this gamma square? It's 1 divided by 1 minus V square by C square. Okay, so you take minus here, so it is simply minus F10. Clear? Okay, so anybody remembers these things? What is F01? So it is electric field in the x direction. Clear? So what will be now F10? It's minus Ex. Okay, so 01 and 10, they are actually opposite to each other. I mean sign change. So it means, so which implies electric field in the x direction. If I go from one frame to the another frame, so the electric field remains in the x direction. It remains same. Okay. So the x component of the electric field does not change. Now let's look. So that means this is a trivial component. Okay. Now let's look at the y component. That's very important. Everybody followed it? Huh? Okay. So you have written it. So now let's take I is equal to 2. So let's take I is equal to 2. So what I will get? So it is F prime 0, 2. So now let's write I is equal to 2. Okay? Look here. So when I put I is equal to 2 here, okay? So it is lambda 20. So lambda 20 is 0. Is that true?
Yes, sir.
So now let's look here, lambda 21, that's again 0. So that means these two terms will not contribute. Now let's look here. You are having non-zero lambda 22 here, is it? I is equal to 2, I is equal to 2. So that means these two terms contribute, is it? And also look here, you are having lambda 23. Lambda 23 is again 0, lambda 23 is again 0. So it means F prime 0. So it's simply equal to lambda 0, lambda 22, F02 plus lambda 01, okay, lambda 22, F12. Clear? So what is lambda 00? It's equal to gamma. What is lambda 22? It's equal to 1. Okay, so gamma into 1. What is F02? What is F0? Okay, let's keep F02 as such. Okay, plus what is lambda 0, 1? It's minus beta gamma. Okay, what is lambda 2, 2? That's equal to 1. So you are having F1, 2. So, or I can write what is F02? It's y component of the electric field. So it's Ey prime. That's equal to gamma times, okay, Ey, okay, because F02 is Ey, minus beta gamma. What is F12? That is Z component of the magnetic field. Okay, so this will be simply Z. So it means you are having Ey prime is equal to gamma into Ey minus beta Z. Clear? So that means, look here. So Ey has what? The magnetic field component with it. Samajhan? So that means when you are moving, okay, when you are looking at a moving charge, okay, so from another frame of reference, let's say if you are having only, okay, you will see actually both electric and if you are having moving charge, if you are looking at it, the same way you are having current carrying conductor, okay, so you are having one conductor, it carries current, is it? So that means it is only the magnetic field, clear? But when you look it from another frame of reference, you are having both electric field as well as, you don't only observe the magnetic field, you observe both what? Electric field as well. Samajh aa? Clear? Okay, we need to calculate actually all these. Since I am calculating 0th component. Similarly, you can calculate now F03. That means which component? Z component. So Z component is again the same thing. When you are having Ez prime, that's gamma into Ez, I think, plus beta. Yes. So it's plus beta Ez. So it is B1. Okay. So it will be plus here. Huh? Okay. So just put here what? I is equal to 3. Okay. You will be getting F03. So these two terms will not contribute. So this will also not contribute this very term. This will contribute. Okay. Clear? So now look here. If you are having now, you are having electric and magnetic field. They are coupled with each other. In other words, they are related to each other. Clear? So they are not the absolute quantities. Okay. When you move from one frame to the another frame of reference, you will see electric and magnetic fields transforming into each other. Okay, or getting coupled with each other. Okay. So now let's look at the magnetic field. How magnetic field transforms. For that matter, what I need. Okay. Okay. So these things I require. Okay, we'll see in a moment. I mean, if we are having purely electric and magnetic field, then we can see. Okay, now let's write this Fij, because ijth component gives me the magnetic. Okay, ijth components of F gives me the magnetic field. Okay, F12 gives me the Bz component, F13 gives me what? X component, and what is F13? That's Y component, is it? What is F23? That gives you the X component of the magnetic field. Okay, now how they will go? So you are having lambda I, okay, lambda J. What was the? Okay, I put lambda sigma. Clear? So you can now put again the sum. Can you do it yourself? Shall I show? Shall I do it here explicitly? Okay, for you people, let's do it. Let's not burden you. Okay, rather overburden you. Okay, so let me do again the sum. So it is lambda J0 F, okay, lambda 0 plus lambda J1 F lambda 1 plus lambda J2 F lambda 2 plus lambda J3 F lambda 3. Okay, now you sum again over lambda. Okay, let's do the sum over lambda. So what it will be? Lambda I0 lambda J0 F00 plus lambda I1 lambda J0 F10 plus lambda I2 lambda J0 F20 plus lambda I3, lambda G0, F3, 0. So it is this very term. Huh? Okay. So let's erase it then. Okay. Plus, so now let's do the other term. So lambda, that's right. Okay, just tell me what will be the terms. Lambda I0, lambda G1, F01 plus lambda I1, lambda G1, F11 plus lambda I2, lambda G1, F21 plus lambda I3, okay, lambda G1, F3. Clear? So plus, then you are having lambda I0 again, lambda I0, lambda G2, F02 plus lambda I1, lambda G2, lambda 12 plus lambda I2, lambda G2, 22 plus lambda I3, lambda G2, F23. Clear? F22, F32. No, tell me. Is there any mistake? Yes. 3, 1. So it is 3, 2. Okay, 3. Okay, 2. It is 3 and so lambda I0, lambda G3, F03 plus lambda I1, lambda G3, F13 plus lambda I2, lambda G3, F23 plus lambda lambda I3, lambda G3, F33. Clear? So these are the 16 terms. Okay. So let me take Z component. So if you take the X component of this very thing, X component will not change. Okay, from here, if you take X component, dx prime is same as what? Dx. Okay. So the way you are having Ex prime same as Ex, here you are having what? Bx prime same as Bx. Clear? So it does not transform. So only the only the components which transform are the X and Z components. Okay, because we are considering boost along X direction. So it is the fields, components of the fields along X and Z and Y direction which get actually transformed. Okay. So now let's take the what is the Z component? Anybody? Tell me. F12. Is it? F12 is the Z component. Let's take. Okay. Before doing that, let's figure out how many terms are 0 here. So this term is 0. Clear? Okay. F11 is 0. F22 is 0. F33 is 0. So the 4 terms are 0. Okay. So now we need to explicitly check other terms. Okay. So from now these are how many terms? 12 terms. Okay. Now let's take F12. So I is equal to 1, J is equal to 2. So what I am getting? F prime 1, 2. Okay. Now let's look. So this is 1. Okay. So this will I is equal to 1, J is equal to 2. Just look here, then you can write. Okay, I is equal to 1, J is equal to 1, J is equal to 2. So you are having lambda 1 1 and lambda 2 0. What is lambda 2 0? That is 0. So this will not contribute. Now again 1 2, lambda 1 2 is 0. Is it? Is that true? Okay. So what about lambda 1 3? It's again 0. So this will not contribute. Now look here. So you are having lambda 1 0, that is non-zero. Lambda 2 1. What is lambda 2 1? It is 0. So this does not contribute. So you are having lambda 1 2, it is again 0. So you are having lambda 1 3, it's again 0. This will not contribute. Now look here. So you are having lambda 1 0 and lambda 2 2. Lambda 2 2 is non-zero, is it? So that means we are having this very term. Okay. Lambda, let me write. Lambda 1 0, lambda 2 2. So you are having F0 2. Now let's look another term. So it will be this thing. Lambda 1 1. Okay, lambda 2 2. Okay, so this also non-zero. So if you see, all other terms will be 0 plus lambda 1 1 lambda 2 2 f1. Clear? So if you look at this very term, so it will be lambda 1 0 lambda 2 3. Lambda 2 3 is 0, lambda 2 3 is 0, lambda 2 3 is 0, lambda 2 3 is 0. Okay? So only these two terms will contribute out of these 12 terms, or rather 16 terms. Okay, so what is lambda 1 0? Minus beta gamma. Okay? So what is lambda 2 2? That's equal to 1. What is f0 2? Okay, or I can write bz prime is equal to, what is f0 2? It's ey. Okay? Plus what is lambda 1 1? It's, what is lambda 1 1? It's gamma. Okay? What's lambda 2 2? It's equal to 1. What is f1 2? It's bz. Clear? So it means, or I write bz prime is equal to, I will write this thing, let me take gamma out, so it is bz minus beta. Clear? So z component transforms in this way. Similarly you can write, okay, by component, so it is gamma into by plus beta bz, like this. Okay, got it? And if you see this bz, sorry, bx prime is same as bx. Okay, so this is how electric and magnetic field is transformed under Lorentz transformation, rather Lorentz boost. Okay. Okay, shall I erase it? So let's write them here. Okay. Okay, so we are having this ex prime same as ex. Okay, ey prime is equal to gamma into ey minus beta bz. Okay, then ez prime is equal to gamma into ez plus beta by. Okay, so these are the electric fields, and then you are having magnetic fields. Bx prime is equal to bx, by prime is equal to gamma into by minus beta. No, it is plus here, beta ez. Okay, then you are having b prime z is equal to gamma into bz minus beta. Okay, so these are magnetic fields. Yes? Any problem? Any question till now? Okay, so okay, now let's look at the special cases. Let's look at the non-relativist limit. First, let's look simplify them. Okay, in the non-relative limit, that means v by c is less than 1. Clear? So since our current carrying conductor, that was actually the non-relativistic system, is it? Okay, so let's take the non-relativist limit. So what will happen? So this gamma tends to 1. Okay, what is gamma? Gamma is simply 1 divided by root of 1 minus v square, 1 minus v square by c square. That will tend to be that will be equal to 1. So it means we are having this thing, ex prime is same as ex, and ey prime is same as what? So ey minus beta bz. Settle it can, whether you are having a relative limit or the non-relative limit, settle it contains what? So this is not 0. It is very small. Okay. So this term is very small, is it? Because beta is very less than 1. So when you are having non-relative particle moving at the slower speeds, so this component will be actually negligible. That's why in Newtonian mechanics you are not able to realize this very component. Although it is there, it's very small. Huh? So this amount is very small. So you are having now Ez component is equal to Ez. Actually, these are the relations which led Einstein to the development of theory of relativity. Huh? Okay, to understand the transformation properties of these electric and magnetic fields. Okay, so then you are having this bx prime same as bx. Okay, by prime is equal to by plus beta bz. Okay. bz prime is equal to bz. So clear? So now let's write the inverse transformations. So you can write actually the inverse as well. So from here you can write the inverse. Let's say you put ex in terms of prime, is it? Let's write ey in terms of ey prime. Just change the sign of beta here, is it? So what will be the inverse transformation? Okay, so or I can write the inverse transform this way. Ex is equal to ex prime. Okay, ey is equal to ey prime plus beta bz prime, and then you are having ez prime is equal to ez is equal to ez prime minus beta by prime. Okay, in terms of primary system. Similarly for the other case. Clear? Got it? Similarly for the other case. What is okay? So we are considering velocity along x direction. Is that true? So since velocity is where? Along x direction. So it means I can write a velocity vector as v0, 0. Let's assume v is the velocity, relative velocity between two frames. Okay, since it's only along x direction, there is no x and y, sorry, y and z components. I'll put v as the vector. Okay, so I can write these three equations in a single equation in this fashion. Okay, vector e. Okay, so this vector e, let me write e is equal to this vector e prime minus v by c. Okay, let's say it is, sorry, it will be 1 by c v cross b. Okay, rather it will be b prime. Okay, so if you make a cross product between v cross b, so what you will get, since v is having only these two components, you will get these two things. Clear? Samajh? And okay, so these you can put as similarly b vector b is equal to this vector b prime minus, I think, plus 1 will be plus another. Okay, so this is plus, I'm sorry, this is plus v cross, okay, plus 1 by c, let me write it is b prime cross of v, this way, let me put this way, minus 1 by c, e prime, cross this. Okay, so these are the two non-relative equations. Clear? So now let's look at the implications of what we have done. What are the implications? Okay. So let's assume case 1. Assume in one frame, frame K prime, we are having b prime is equal to 0. In frame K prime, we have a b prime is equal to 0. What does that mean? It is when you are having magnetic field equal to 0, what does it mean? You are having only electric field. Since I am taking both electric and magnetic fields, I am considering a frame of reference where magnetic field is 0. So you are having entirely what field there? Only electric field. So it means we are having purely electric field. So you don't have in that frame what? Magnetic field. Okay? So when you are having purely electric field, okay, b prime is equal to 0. Okay? So it means, so this means what? E is same as E prime. Clear? Now let's look at the second equation. Figure out the magnetic field in the another frame of unprimed frame of reference. So in the, okay, I am having electric field this way. Okay, now what will be the B? So in that, which implies, so the magnetic field in the unprimed frame. Okay, I am having primed frame, there is magnetic field is 0. Now I will look at it in the unprimed frame of reference. The frame of reference which is moving with respect to this primed frame. Okay. So in that case, what this B will turn out to be? It is simply minus 1 by C Okay, E prime cross V. What is E prime? So let me write E prime cross of V. So that is same as what? E cross V. So is this 0 or non-zero? So E is non-zero, is it? So that means if you are if you observe a static electric field, there is no magnetic field at all. So in another frame of reference which is moving with respect to that field, okay, so you will also observe the magnetic field. Okay, so think of a static charge. If you are having a point charge, it's at rest. Okay, so you are having the field is purely electrostatic in nature. Clear? So there is no magnetic field. Now an observer is moving with respect to that point charge. Okay, so what he will observe? He will observe magnetic field as well. Okay, because electric and magnetic fields are relative in nature. Okay, motion is relative. Clear? So the amount of magnetic field that he will observe is this thing. So it will be simply 1 by C. Let's say V cross E. Now let's look how much it is. Let's take the magnitude of this magnetic field. Okay, so it will be 1 by C V. V will be the magnitude. So the magnitude of electric field. Now what is V by C? It is beta, is it? So it means this magnitude of B, let me write simply B, okay, which implies this B is less than what? In this frame of reference, what is B? It's less than electric field. So that's why when you are moving in the non-relative speeds, you are not actually able to observe that magnetic field. Okay? If your electric field is, let's say, very weak, you will not be able to observe what? This kind of magnetic field, because we are in the non-relative limit. You can do it in the relative case as well, but it is easier to understand here. Clear? So now let's take what is the velocity here in this case. So when you are in this case, we are having this V is equal to B CB divided by E. Clear? Okay, now let me take again this very relation. So you are having this B is equal to 1 by C, okay, V cross E. Let's make a dot product with E. So E dot D, it's equal to 1 by C E dot V cross E. Now tell me, what is this triple product equal to? 0, because two vectors are same. So what it means? So when you are moving in a frame of reference, okay, when you are moving with respect to a frame which is having only electric field there, okay, when you are moving with respect to a static electric field, okay, the moving frame will always observe what? Both electric and magnetic field, and those fields will be perpendicular to each other. And the velocity will be given by simply B by E ratio. Clear? So think of now these conductors, two parallel conductors. So you say they attract or repel each other. So that means there is a work done. Okay, now what component will be held responsible for that? It will be actually electrical, because if you take one, let's say, steady state current, so that means purely magnetic field, there is no electric field at all. So but the other observer in the another conductor, that will observe both electric as well magnetic field. It will be actually the electric field component of the electric field that's responsible for the attraction or the repulsion between the two conductors. That means the work done due to this force of attraction or the repulsion. Clear? Okay, now let's look the another case. Okay, so if you are having now E prime is equal to 0, let's say it is case second. So we have, so E prime is equal to 0. That means what? Purely magnetic. So it implies B is equal to B prime. Clear? So from the second relation. So now you are having purely magnetic field, no electric field at all. What you will observe from the first relation? So which gives me the electric field in the unprimed frame. Okay, so this is in K frame. Right? E is equal to 1 by C B prime cross of V. What is B prime? It is same as B. So it will be B cross V. Okay. So now tell me what is the magnitude of electric field here? So that is simply V by C, magnitude of B. So it implies in this frame. So when you are having purely electric field, when you are having purely magnetic field, in a moving frame of reference, you will observe an electric field that's weaker than the magnetic field you started with. Clear? So much more? Okay. So now tell me what is the velocity? So velocity will be simply C times E by D in this case. Okay. So now again, let's take the dot product. So if you take B dot E, okay, so what that will be? Again 0. Because when you take B dot, so two vectors will be same. So it means you will observe again electric and magnetic field to be orthogonal to each other. Okay? Clear? Samajh aaga? So any question? Okay, so this is all about okay, so now you have calculated actually the electric field on a moving charge, electric field due to a moving charge. Is that true? So how you can do that? Now let's say if you are having a moving, you start with a moving charge, okay? Or you are asked to be what is the electric field due to a moving charge. How you can think of a moving charge? You think moving charge, you have actually applied a boost on a static charge. Is that true? So let's say I am having a moving charge and I am asking you to figure out what electric field or the magnetic field due to this moving charge. Clear? How you can calculate it? At the first instant you will assume the charge is at rest. Okay. Then you have applied a Lorentz boost along x direction. Let's say. Okay. Then you know how electric and magnetic field components transform. Is it? So you need to know what is the electric and magnetic field when it is at rest. Is it? So you are having only one component at hand.
Yes, sir.
Clear? Only one component or three components. Only the electric field components are there, because let's say if you are having a point charge at rest, what is the electric field? Let's say Q divided by R square and unit vector R. Is it? So these are okay. So along three directions you are having Q by R square as this thing. What is the magnetic field? It's equal to 0. Now when you move to where? Moving frame, so you need to calculate these components. Okay, so try to do this thing. It's a very nice exercise. Okay, figure out what is the electric field due to a moving charge. Okay, let's say you are having a charge of Q, it's moving with certain velocity. Okay, so you calculate the electric field. Clear? So try to do it in this fashion. Okay, so you need to take care of this R is actually changing as well, is it? So because when you apply the boost, what will happen to R? There will be a transformation as well. So you do it. So think of it. If you are not able to do it, I will do it. Okay, how much time is there?